Have you ever just stared up into that big blue sky and wondered, where does it all end? Well, today, we're taking a journey straight up, climbing through the invisible layers of our atmosphere to really understand the complex and, honestly, fascinating structure of the sky above us. So, let's start climbing. Right? It's a question we've probably all asked at some point. The sky feels absolutely infinite, like this endless ocean of air. But the reality? It's actually way more fragile and surprising than you'd think. The entire system that keeps us alive, warm, and protected is, when you see it from space, incredibly thin. Just let that sink in for a second. If the Earth were the size of an apple, our entire atmosphere would be as thin as its skin. Every cloud, every storm, every single breath you've ever taken, it all happens in this paper-thin, delicate layer. It's such a powerful way to visualize just how precious this blanket of air really is. Okay, so here's our flight plan. First, we'll start in the dense, weather-filled layer we all call home. Then, we're going to ascend through the calm region where jets fly and the crucial ozone layer lives. After that, we'll push into the real frontier of space, where meteors burn up and auroras glow. Before finally, we'll zoom out and see how this whole thing fits together.
All right, our journey begins right here, at ground level, in the layer we know best, the troposphere. This is our world. It's the stage for pretty much all of human history and all of Earth's weather.
The troposphere is really where all the action is. It goes up about 16 kilometers or 10 miles. If you've ever seen a cloud, or felt rain, or heard thunder, you've seen the troposphere at work. It is by far the most dynamic and densest part of our entire atmosphere.
And this is what drives all our weather. The sun heats the ground warms the air right above it, and that warm air starts to rise. But as it gets higher, it cools down, gets heavier, and sinks back down. It's kind of like a pot of water on a stove, just constantly churning. This motion, called convection, is what gives us wind and clouds and storms. And that lid at the top, the tropopause, that's exactly why passenger jets fly so high, to get above all that turbulence and find some smooth air.
So, based on what we just learned, you'd think so, right? I mean, you climb a mountain, it gets colder. You go up in a plane, it definitely gets colder. But the atmosphere has a pretty big surprise waiting for us just above those clouds.
Welcome to the stratosphere. It stretches from where the troposphere ends all the way up to about 50 kilometers. And up here, the rules totally flip. Instead of getting colder, it actually starts getting warmer the higher you go. So what in the world is going on?
It all comes down to one absolutely critical feature, the ozone layer. Think of this layer like a planetary sunscreen. It absorbs most of the sun's harmful ultraviolet radiation. And when it absorbs all that UV radiation, it's also absorbing energy, and that energy heats up the air in the stratosphere. It's a simple but totally vital process that protects all life down on the surface.
This chart really nails the difference, doesn't it? We go from the turbulent, churning troposphere, where it gets colder as you go up, to the calm, stable, and warming stratosphere. And because there's no churning motion here, the air is super stable. Now that's great for airplanes, but it also means that if pollutants manage to get up this high, they can just hang out there for years.
And speaking of planes, this calm layer is home to the jet stream. These are basically super fast rivers of air, just whipping around the globe at hundreds of miles per hour. Pilots can actually catch a ride on them, like an atmospheric conveyor belt, to fly faster and save a ton of fuel. And they don't just help planes, they play a huge role in steering weather systems around the planet.
Okay, let's keep climbing. We're now leaving the parts of the atmosphere that feel familiar, and we're entering the true frontier of space. This is where the sky puts on its most spectacular shows.
We've just reached the mesosphere. You can think of this layer as our planet's fiery shield. The air up here is incredibly thin, but it's just thick enough that when tiny bits of space rock come hurtling towards Earth, the friction makes them burn up in a flash of light. Every single shooting star you've ever wished on is a meteor vaporizing in this protective layer.
But here's the twist. While it's a fiery shield from meteors, the mesosphere itself is absolutely freezing. At its upper edge, temperatures can plummet to negative 90 degrees Celsius. That's about negative 130 Fahrenheit. It is the coldest natural place anywhere in Earth's atmosphere.
Now, above all that extreme cold, we enter the thermosphere. And guess what? The temperature trend flips again, skyrocketing to incredible highs. This is the home of the awe-inspiring Aurora Borealis and Australis, the northern and southern lights. It's also where the International Space Station silently orbits the Earth, gliding through this incredibly thin air.
Okay, now here is a really cool paradox. While the temperature up here can be thousands of degrees, an astronaut on a spacewalk wouldn't feel hot at all. Why? Well, temperature is just a measure of how fast molecules are moving. And the few air molecules that exist up here are moving incredibly fast. But they are so far apart that they would almost never actually bump into you to transfer any of that heat. It's a weird concept, right? And finally, we reach the exosphere. This isn't really a distinct layer so much as it is a slow fade to black. Here, our atmosphere just gradually bleeds away into the vacuum of space. Individual atoms of gas are so far apart that some of them just drift away for good. There's no hard border, no welcome to space sign, just a final, quiet thinning of the air until it's gone.
So, we've climbed through these completely different worlds, from a churning weather factory at the bottom to a silent, freezing shield, and then a superheated light show at the top. But how do they all connect? Let's zoom out and look at the big principles that unify our entire atmosphere.
First up, let's talk about air pressure. Just look at how dramatically it drops as you go up. By the time you reach the summit of Mount Everest, you're already above more than 2/3 of the atmosphere's entire mass. In fact, about half of all the air is packed into just the first 5 kilometers. It really brings home just how thin that apple skin truly is.
And the second big idea is composition. Despite those wild swings in temperature and pressure we saw, the basic recipe for air stays remarkably consistent, at least to the lower layers. It's mostly nitrogen, with a good bit of oxygen and a splash of other gases. This tells us it's not what the air is made of that defines each layer, but how that air behaves under different amounts of energy and pressure.
And this, right here, is really the main takeaway. Our sky isn't just one uniform thing. It's a stack of totally distinct environments, each with its own rules, its own personality, and its own vital job to do, from that churning weather engine at the bottom to the glowing frontier of space at the very top.
So, the next time you look up at the sky, maybe you'll see it a little differently. You'll see the churning troposphere in the clouds, the clear, calm blue of the stratosphere beyond, and imagine that invisible, freezing cold shield way, way up there, protecting you. So I'll leave you with this thought. The next time you see a shooting star streak across the night, which layer will you remember to thank?